HW5A1, we're going to be deriving the Gibbs, not the Gibbs energy, the Gibbs phase rule, which tells you about the amount of unknowns you can have, which depends, as I will show you, on the amount of phases and the amount of substances or different substances a part of your system. So first, we need to do a quick review, and let's look at Raoult's law. So Raoult's law is for perfect mixtures. Again, mixtures and perfect are the only two words very important. And it is xi, which is the mole fraction of one of the phases, times the pressure I of the sat, actually not one of the phases, of the liquid phase, times the saturation pressure at a certain temperature, equals yi, which is just representative of a number, times pressure, which this gives us the partial pressure of this substance right here. And now, after we've gone through that, let's look at this small diagram I drew. So in here, we have two substances. We have toluene and water. And the substances right now, they aren't specific. I'm just using them as an example, but they can represent different things when actually trying to solve numerically, as they will have different Gibbs energy values. And so here we have our vapor phase, then we have our liquid alpha phase, and then we have our liquid beta phase. Excuse me. So if you're wondering why we have two phases, it's because we could have an oily liquid mixture in between our liquid phase and our vapor phase, and so that sometimes is how we can create three phases by only having two substances, and neither of them are solid, as that would kind of defeat a mixture. And something about this system that is interesting is that you can calculate the chemical potential value. And so we're going to call that mu. So we're going to call mu equals Ng d over dn. And what this means is what this actually means is that we're going to put an I there just so it can be any value. Is that you can think of this as the Gibbs energy per mole. Well, this isn't exactly that. In fact, it's an easy way to think about it. And this is really important because before I get ahead of myself, one thing we want to make sure we know are the different mole fractions or how that affects this system. So in each phase, there's going to be a mole fraction of whatever substances we have in there. And so, for example, each mole fraction, when you add up, as we only have two values, these two values, then their fraction form, should equal 100, or not 100, should equal 1 if we're going to be using that in 0.95 or 0.5 as the percent of our substances. And again, this is important as this is just simple algebra, but it's really important to understand that each phase has a different mole percent or a different mole fraction, as if they have the exact same and they don't add up to 1, you're going to have a lot of issues, as that's technically impossible. So now, as I was saying, we have our chemical potential. And chemical potential shows that we're going to use, I'm just going to write T as the subscript to designate its toluene. That the mu, we're going to use L beta toluene equals U toluene of L alpha, which equals mu toluene of the vapor phase. And so, over here, I'm going to write this is the change in Gibbs per mole. And another thing, before I keep getting ahead of myself, is that we keep N, as we're going to be finding, this has to be done in a mixture. That means you have to keep the other value constant. The other, not the value, the other N value, the other mole constant. And you also have to keep temperature and pressure constant. As these changes, as you can see up here, if you multiply the temperature and the pressure, these the mole fractions will change. And so you can't have the mole fractions changing if we're trying to keep them constant, which will then affect our chemical potential. But back to this, what this states is that the Gibbs energy in each phase is the same as, this is in per mole basis. And so, if we have 5,000 moles, it's going to be the same as 1 mole, as that's our dividing factor. We want it per mole basis. And so, what you can do with this is you can start calculating how many equations or how many how many different phases and equations you're going to need to calculate a certain amount of unknowns. And so, let's talk about intrinsic unknowns or intrinsic variables. Intrinsic variables are variables that are not affected by the size of our, say, a reactor. And so those intrinsic variables are going to be the phases, or let's write this. So we're going to call that V. It equals the mole fractions. And so for the mole fractions, for each fraction, you're going to have a phase, right? So we're going to do phase, or P, and then we're going to do C minus 1, excuse me, C minus 1 plus 2. And the reason I am adding this plus 2 is because for intrinsic variables, as we just stated, temperature and pressure are held constant. And so that's where this will come in. And what we have here is P, right over here, is not pressure. P equals the number of phases. Just like how I'm going to be using C as the number of components. And we're using these as the number of components. Well, obviously, these are important as, so if the number of variables, we're going to multiply by the amount of phases, and these are phases that don't, these are variables that are not affected by the amount that is in our system. They are kind of on a per basis. So we have our amount of phases multiplied by the amount of substances, or the amount of components, and then we're going to subtract 1. And we're subtracting 1 is because if we have the components of all the other variables, right, or we have all the other variables on a per phase basis, we know that mole fraction has to equal 1. And so we can actually calculate that one last value. And so that's why we have C minus 1. And now we want to calculate the number of equations we need. And something to make note of is that we have UT, or L beta equals L alpha equals V. And so that's not so different as writing L beta equals the V value for our chemical potential. And those are all one equation. Those do not equal 2 separate equations, which is important to note. So our next we are going to write is the number of equations, and we're going to multiply that by C, or the amount of components, right? As we have the components, it depends on each component. Okay, and we're going to multiply that by 1 minus P. So there was a slight mistake when I was writing the equation formula. What it should be is that the amount of components multiplied by the phase minus 1 should equal the amount of equations we should be getting. And this is because we have C, or the amount of components, which again, if you need to remember it, we're going to have each of the components in each phase, even if it's a minute amount, multiplied by the amount of phases subtracted by 1. And we're subtracting by 1 because this right here is 2 equations. However, you can write it as 1, but it then leaves out an extra value. And so if we subtract by 1, we are essentially getting the exact same formula, except we're getting rid of this like a pesky extra value that we already know as it's the same as the others. And so now that we have this formula, what we want to do is subtract the two values to get our Gibbs phase rule. So we're going to get PC minus P plus 2 subtracted by, that's going to be CP, and PC and CP are the same thing, added, plus C. And so our CP's cancel, and we're going to get the amount of components minus the number of phases plus 2 equals our Gibbs our Gibbs freedom analysis equation. And in the next steps, I'll show you how to use it while showing you with water at a triple point, water while it coexists with vapor and liquid, and then also when ethanol coexists with water, I believe. But this is the equation that we just derived, and I will erase the board, write it on the side, and we will be able to go again. Now, we are going to use our degrees of freedom analysis to calculate or show how many degrees of freedom or how many variables we can pick and choose at the triple point. And so, if we're going to use the triple point, but if you remember from the earliest videos, it has to be a pure substance. And so we're going to have one component minus, the pressure, P, minus the amount of phases, and so that's 3 plus 2. Which equals a grand total of 0. And this is because the triple point is just picked by nature. You can't do anything to change the triple point. You have the triple point here, and it is set. You can't move the temperature. Oh, now you're on this equilibrium. Oh, you change the pressure. Now you're on this equilibrium. Oh, you drop both. Now you're over here. And so it's really it's interesting, but you have 0 degrees of freedom if you want to be at the triple point. There are set points that you have to follow. There's very minute discretion for error in that. So now, what are we going to do if there's vapor? Again, it's going to be using pure H2O vapor and liquid. It's all pure water, but it's going to be on the equilibrium between vapor and liquid. That means, again, we have one component minus 2 phases plus 2. This gives us 1 degree of freedom. And you might be wondering, oh, how does that work? So let's just draw this graph again. We got temperature, we got pressure. This is a very crude drawing. We got our vapor, liquid, and solid. We don't care about this right now. And what this is telling us is that we have 1 degree of freedom, which means we can pick and choose 1 variable. And so yes, there's going to be a range of temperatures we can pick, or there's going to be a range of pressures we can pick, but we can still pick a variable at a certain value. So let's say, screw it. We are going to pick this temperature. Well, this curve that's already on this graph shows us what pressure we're going to be at, which is what 1 degree of freedom means. We want to be at this pressure right here. And if we go over and find this curve, we're going to find that it directs you to 1 exact temperature. And so 1 degree of freedom means you can pick and choose 1 variable. However, the rest of your variables are already, how's the best to say it? Already designed by God to be given to you, or designed by nature, as you can't really do anything. You can pick 1, but it's not going to change the rest of these variables. Now we are going to be calculating the degrees of freedom for a container like this that has ethanol and water in it. And so let's calculate the degrees of freedom, and then I'll show you, then I'll mess with this a little bit. So we have 2 components. So we have 2 minus the different phases. We have 2. So minus 2 plus 2. This gives us 2 degrees, which equals 2 variables we pick. And before this, now let's look back at our tank here. We know that we're going to call ethanol 1 and water 2. We know that x1 plus x2, that equals 1, as these are the mole fractions. Same we know that with y1 plus 2. and that those equal 1. Because again, these are the mole fractions. And so let's look at Raoult's law. If we have xi times pi equals, not pi, P temperature, this is the saturation temperature, equals Y1P. Well, now, let's say we're going to pick temperature and pressure to be our constants. We're going to have two equations for each phase, right? Or for not each phase, for each substance. And so, that's an ugly T. I'm going to redraw that real quick. And so, this is our first equation. We're going to say that we know P and T. This gives us our second equation. As we know, 1 minus x1. This is going to be for x2, by the way, or for x2. This is going to be for, substance 2 times P temperature, P saturation, equals 1 minus y1 over the pressure. Well, we know these. If we know x1, that will give us x2. Same with y1. And based on this, we can calculate, if we so wanted to, and given us ourselves numbers, we can calculate y1, or there's all of the mole fractions in general. If we are just given the temperature and the pressure, just based on this general equation, which again, I want to make sure everyone remembers because I had trouble remembering. So we have, on the right side of this equation, we have y1 times pressure. Actually, I'll go over here just because it's bigger. And so y1 is the mole fraction that is in the y, or the vapor as we're calling it right now. And then this is the total pressure. But if you multiply these together, you get the partial pressure of that substance. And so when you add up, if you add those partial pressures, you end up getting the total pressure, which is, again, another way we can calculate that. And again, let me just run through this real quick. We have two components, two phases, gives us 2 degrees of freedom, and we can write out using Raoult's law, which is make sure it's a perfect mixture and it's ideal gas, that we have these two equations of x1 equals P saturation at a certain temperature, which we picked because we have 2 degrees of freedom, equals y1, the mole fraction in the y, times the total pressure, which we also picked as to remain constant, or to remain known to us or constant. And so now, we can use our x values, our mole fractions, to calculate the other mole fraction and write our second equation for the other, what's it called again? For the other component, yes. And I believe that is all for homework 5A